All right, so in the last video, I introduced this thing called the t-distribution. What I want to talk about in this video is what is 5.1 in our book, and this is where we learn two calculator functions, one called t-test and one called t-interval. And what you'll see is that these two calculator functions kind of correspond with z-test and z-interval, the way that we did hypothesis testing and confidence intervals when we had numeric data in the past and we were given sigma. If you're not given sigma, you can't use z-test and z-interval. You instead use t-test and t-interval. And you might be like, oh, yeah, okay, but what about inverse norm and normal CDF? Right? We've really done three different things with the z-distribution so far. Confidence intervals, hypothesis testing, and this stuff with probabilities, inverse norm and normal CDF. Turns out you can do all three with the t-distribution, but in our class, we'll only do hypothesis testing and confidence intervals. And that's because of a weird little feature with your calculators. If you hit second and then variables to get into the distribution menu, here's the familiar normal CDF and inverse norm. This specific calculator you're looking at right now has a t version of normal CDF. It's this t-CDF function. And it has a t version of the inverse norm calculator function. It's this inverse t. All right, so 4 and 6 kind of take the place of 3 and 2 in the past. And that works out great on this calculator. But if you have an older calculator and you go to the same screen, what you'll see is this one, this one does have t-CDF, so I could do the t version of normal CDF questions, but there is no inverse t. And some calculators, if they're even older than this, won't even have this t-CDF function. So because different calculators will have different things available to you, I don't even want to bother with this stuff because I don't want to put somebody who has an older calculator at a disadvantage to somebody who has a newer calculator. So we're not going to bother with any of the t versions of inverse norm and normal CDF. We won't even bother. You can do them, it works, but we won't bother. I'm going to assume that you learned enough in 4.1 and 3.1 with these two calculator functions that you don't need to learn it again, the t version of them. But we will do t-tests and t-intervals, and maybe I can start with an example. All right, so example 1. Let's say that in a random sample of, I don't know, let's say 100 chocolate chip cookies. I'll be a little lazy here. The average number of chocolate chips is, I don't know, 40, sure. With a standard deviation of 10. Fine. I don't know if those are anywhere close to realistic, but who cares? In a random sample of 100 chocolate chip cookies, the average number of chocolate chips is 40 with a standard deviation of 10. Maybe I ask you to create a 95% confidence interval for the average number of chocolate chips in all chocolate chip cookies. You might look at this at first glance and be like, oh, I've done this before. Like, this is really easy. I know how to do this. There's one thing that's really subtle in here. If you read through this problem, a random sample of 100 chocolate chip cookies. That's our sample size. We've been using the letter N for that. We still will. The average number of chocolate chips is 40. It sounds like a sample average. This average just refers to these 100 cookies. So there's X bar right there. With the standard deviation of 10. That's the thing that's different. Right? That 10 right there is only referring to these 100 cookies. It's not saying I somehow know the standard deviation of the number of chocolate chips in all cookies is 10. This is not giving you sigma. This is giving you S. The sample standard deviation is 10 in this case. And that's really important. If you read through this problem, it's asking you to make a confidence interval for the average number of chocolate chips in all chocolate chip cookies, but we don't know sigma. And so what that means is you cannot use the z-interval function on your calculator. I'm going to write down shape, center, and spread, but what you'll see is that as we move into chapter 5, I'm less interested in asking you these questions. So don't expect to be asked shape, center, and spread in chapter 5 like you were in chapter 4, but I still want to talk about these three ideas in this first example. So the shape here is going to follow a t-distribution. So the idea, even though we don't have any idea what the shape is of the number of chocolate chips in an individual cookie, the sampling distribution is still going to be symmetric bell-shaped because our sample size is greater than or equal to 30. We still have that same criteria. And you're like, I thought that made it normal. I thought that made it a z-distribution. Well, it does if you know sigma. But if you don't know sigma, but n is still greater than or equal to 30, then it's going to follow a t-distribution. It's worth pointing out that if n were not greater than or equal to 30 and we did not know the shape of the parent distribution, we could not use a t-distribution. So just like in the past, we needed our sample size to be large enough in order for it to follow a z-distribution. We still need that. It's just that it won't be a t-distribution. Maybe you could say something like t-distribution because n is greater than or equal to 30 and sigma is unknown. Right? We still need either the parent distribution to be normal or our sample size to be large enough. Still need that same criteria we needed before. But if you don't know sigma, that doesn't make it a z-distribution. It instead makes it a t-distribution. This is true, but don't expect me to ask you to write this on a quiz. Maybe I ask you like a true-false question on the final, something like something about the shape. I don't know. Would this follow a z-distribution? You're like, no, it'd follow a t-distribution because sigma is unknown. Anyways, that's the shape. Center is the exact same as it used to be. When we're making confidence intervals for mu, the population average, we've been using x bar as our point estimate, and we still do. X bar still equals 40. Spread is similar to what it used to be. So in the past, when we were doing confidence intervals in 4.2, we took sigma and divided by the square root of n. And the reason why is sigma talked about the spread of chocolate chips in individual cookies. But we had to divide by the square root of n because we were talking about the sampling distribution. We're still talking about sampling distribution down here. So we still want to divide by the square root of n. However, it's not going to be sigma divided by the square root of n. It's s divided by the square root of n. Because a t-distribution, your spread is given with s here. So s divided by the square root of n, 10 divided by the square root of 100, which in this case is 10 over 10 or 1. So for shape, center, spread, it's slightly different, but kind of the same ideas. But again, I'm not going to ask you that. What I'm going to ask you to do is sketch your picture. And I'll say, make sure that your picture, maybe we can do this higher up, includes your point estimate, your level of certainty, and the bounds of your interval. So your point estimate, just like we've seen in the past, is 40. It goes in the middle here. The level of confidence we have is 95%. So I shade in the middle 95%. And then define these bounds. Well, in the past, you went to your calculator and you hit stat and went over to tests and selected z interval. But if you select z interval, you'll see that your calculator needs to know what sigma is, because you can only use z interval if you know sigma. And we do not know sigma, we know s. If you instead select t interval, the 8th thing listed here, your calculator would be like, oh, t interval, you mean you got t distribution? Well, then just tell me what s is. Note it doesn't ask for sigma, it asks for s. So I give it x bar, which was 40. And then I give it s, which is 10. And then I give it n, which is 100. And tell it my level of confidence, 0.95 in this case. And let it calculate for me. And you'll see that it takes a little bit longer because the t-distribution, the calculations are a little bit more complex. But it figures it out and it gets 38.016 and 41.984. And this is my bounds. So this would be the first thing I would ask you to do. This is not required. And the second thing is I'd say, all right, tell me what that means. And your conclusion is the same conclusion as it used to be. You'd say something like, I am 95% sure or confident or certain that the average number of chocolate chips in all cookies, we're talking about the population average, maybe in all chocolate chip cookies, is between, and these two bounds that we had, 38.016 and 41.984. Couple comments before I end this video. I'm going to do just t interval in this video. We'll talk about t-test in a future video. Couple comments. We had statistics about the data here. I've mentioned several times that you can do these problems if you have the data itself. So imagine I had 100 observations. Like I went out and did a study, and in the first cookie, there were 45 chocolate chips. And in the second cookie, there were 40 chocolate chips. And in the third cookie, there were 41. And in the fourth, there was 32. And I have this big long list of 100 observations. right? If I had some big list of 100 observations, I could put that into my calculator, stat, and then edit, and start typing in these numbers. I'm not going to actually type man, I'll just put some fake data in there. And then I could select stat and tests and select t interval again. Note it would still be t interval because I would not know the population standard deviation. This would be all the information that I have. I select t interval, and you're like, it asks you for x bar. How do you know what x bar is? Well, you could go to one variable statistics, and it would tell you x bar and s. But why would you need to do two different calculator functions? Why would you have to do one variable statistics and then type those numbers in? It'd be nice if you could just tell your calculator the data itself. You can. Just tell your calculator that, yeah, I got data and I put it in L1. Make a 95% confidence interval out of that data that's in L1. And you hit calculate and it does it for you. These are just going to be nonsense numbers because the data that I put in L1 had no meaning at all. But if you put in your 100 observations, and there are the 100 observations that produced these statistics, you'd get exactly this output here. So the point is just maybe it's more realistic to have actual data, not to be given statistics about the data. And yeah, you can do that, and you'll see that pop up every once in a while in the homework. But I kind of take this contrived position where typically I give you statistics about the data because I trust that you could do this. There's nothing extra in what we just did here. It's just tedious on the student's end if they have to enter a bunch of observations. But you'll see once or twice in the homework that you have to actually put in the observations. Now you've seen how. One more comment before I call this good. If I had hit stat and went to t, or I did go to t interval. If I hit stat and went to z interval instead, and put in the same stuff, right? I put in, said that I have statistics about the data, and it asks me for x bar, and I said x bar was 40, and it asked me for n, and I say n was 100, and then it asks me for sigma. And suppose that I put in the value of s here. If sigma were 10 and I made a 95% confidence interval, it would give me an output that is very similar to what you see here. Almost identical, 38.04 to 41.96, almost the same as what you see here. The only difference is what I got out of the t interval is slightly wider than what I got out of the z interval. And that makes sense because the idea is if I know the true value for sigma, then this is exactly how far I need to go to capture 95% of the observations. But if I don't know sigma, and instead I'm just estimating that with s, well, s might be wrong. S is just a guess at sigma, so I better go a little bit further. I better make a slightly wider interval in order to make sure that I get 95% of the data. It's very slightly wider because S is such a good estimate for sigma because my sample size is so large. But maybe that shows you the slight difference between Z interval and T interval. It's worth pointing out that you're like, oh, this is close enough. If I put this on a test, I'll get it right, right? No. Because I'm not going to ask you about shape, center, and spread, it's very important that you tell me these exact values so that I know that you know that it's a T distribution. You might even want to write up here, I use T interval to make it clear to the grader that you're using T interval and these are the answers that you're getting. And you know you're using T interval because what you're given is S here and not sigma. That's all I got.